So hello everyone, welcome to MagNetZ. So today I'm pleased to present Facundo Sapienza, who's a postdoc at Stanford, and he's going to be telling us today about using physics-informed machine learning to estimate apparent polar wander paths. All right, take it away, Facundo.
Well, thank you everyone. Thank you the organizers for the invitation, and thank you for the people here in the room. Today I'm going to be talking about physics-informed machine learning for apparent polar wander path estimation, kind of a work that I started at the end of my PhD a year and a half ago, and I'm going to be presenting these today. So I thought a good way to start would be maybe to introduce a little bit about myself. So I'm a scientist from the soccer nation of Argentina, drinking mate all the time, but probably most important in terms of research, my research kind of falls into these intersections of machine learning and statistics, where my background is specifically applied to geoscientific problems. So today I'm going to be talking about paleomagnetism, but large part also of my research is about applications of physics-informed machine learning in the field of glaciology, in the fields of ice modeling. And a lot of the things that I do as part of my research are related to the development of scientific computing tools and reproducible packages, an activity that I mostly do in the Julia Python ecosystem, and with a lot of synergies from the Jupyter ecosystem. So probably a little bit of this talk is also going to be about software reproducibility and open science. I did my first research project at the University of Buenos Aires in paleomagnetism. That was my first project back in the days. I'm still working in paleomagnetism, so I always like to say that you always come back to your first love, as the famous the tango from Carlos Gardel says. So I'm still around, and hopefully going to be around for a couple of more years, because I really like this field. So any question, any suggestion, it's more than welcome. One of the things that I like to give this presentation is to connect with new people. But let's start with the basics. What do you mean? What do we mean when we talk about physics-informed machine learning? So probably most of you already heard about machine learning methods and AI. In general, traditional machine learning methods we label as black boxes because they usually lack interpretability, which is very, very important in science. Example of these methods are neural networks, random forest, XGBoost, any machine learning methods you're familiar with. So if we draw this line where in one extreme we have theory or physics-based models, and on the other side we have data-driven models, most of the cases machine learning method falls into the right-hand side of this edge, into data-driven models. Very common problems that fall into this category is what are called regression problems. So in statistics or machine learning, when we talk about regression problems, it's just the general formulation of predicting some response Y as a function of X, just based on data. However, the sciences, the natural sciences specifically, I usually describe as some underlying physical theory or model. For example, describe in terms of differential equations or in terms of physical constraints we have in the system we are studying. So the idea of physics-informed machine learning is kind of like standing between these two philosophies and develop data-driven methods that can include physical knowledge into their design. For example, through differential equations constraint. So what I'm going to be talking about today, it's about a physics-informed machine learning method. So an algorithm that falls in the middle point between data-driven and theory-driven approaches for estimating apparent polar wander path. There is a preprint if someone is interested in keep reading about this, and this is a work done collaboratively with my collaborators here listed. So what are apparent polar wander paths? So probably most of you are familiar with this. Paleomagnetic data are usually organized and assembled in the form of apparent polar wander path that represent the time-dependent position of the Earth's spin axis with respect to a block of lithosphere. So for example, in this picture on the right, you can see back in the time how the North American continent have been moving, have been drifting. And here around the North Pole, you can see how if from the system of reference of that plate. Instead of the plate moving, we can describe the pole moving, and under the assumption that the time average magnetic field is aligned with the spin axis, we can use this information to reconstruct the past movement of a tectonic plate. Apparent polar wonder paths have been in the literature and are very important for many reasons. The first reference that I found to apparent polar wonder path goes back to 1954 from this paper by Krier, Irvine, and Runcorn, when you can see an apparent polar wonder path with just a few poles for different continents. But the literature is pretty much full of apparent polar wonder path, when in all these cases, the goal is to reconstruct the path, the trajectory of paleopoles in geological time. How do we fit an apparent polar wonder path? So in the most general sense, we are going to be thinking that we have this sphere, and we are going to be describing the time change of directions in the sphere, what we refer as paleopoles. So these little crosses in this plot represent the position of poles in a different time. So each one of these crosses have a different age assigned to them. And we want to kind of fit like a trajectory, a path that goes through them. The difficulty in terms of statistical modeling is that these observations fall into the sphere. So that different names in the literature to refer to this, manifold learning or just directional statistics. But the idea is that the observations themselves are constrained. So traditional regression methods like just linear regression, polynomial regression, cubic splines don't naturally apply in principle in this setting. There are two very common methods used in the paleomagnetic literature to solve this problem. The first one is the classical running mean, which involves taking a time window, giving an age, just taking a time window around that, let's say around 20 million years, collect all the poles in that time window, take the Fisher mean and use that as an estimate for the apparent polar wonder path at that time, and just move that window back in time and reconstruct this path. So in the top here, I'm showing two reconstructions of the apparent polar wonder path of Gondwana. The top right one is using the running mean. So you can see how this technique allows you to kind of reconstruct this apparent polar wonder path. By the way, this is based on the collection of paleopoles from Torsvik et al. 2012. And this other plot, the one on the bottom left, it's using the splines regression technique, which was introduced by Jupp and Kent in 1987. It's also very popular. And it kind of gives you like the major features of the path are, of course, the same, but there are a couple of differences. In particular, you can see like it's in general a little bit more smooth. So these are two very common techniques to fit apparent polar wonder path. However, when you see this path, or when I see this path, I think like a couple of things that shine, or they're still like worth investigating in these plots. One of them is like what's happening here near the South Pole, when you see like some wrangling on the apparent polar wonder path over itself. And then as we approach the Ordovician-Thuringian boundary here, we see like there is one particular pole that produces the apparent polar wonder path to make like a drastic change. So in all these cases, this can be physically being explained. And there could be scientific evidence to suggest that actually this is the real apparent polar wonder path. This really approximates what the pole was doing. But it could also be an artifact introduced by the fitting procedure. So a lot of what I'm going to be talking about here is like, how can we address this problem of distinguishing what could be a statistical artifact versus what can be like a real pattern in the signal. Now, both the methods that I just described have different problems. First of all, they are both designed to fit the trajectory of the apparent polar wonder path. In the case of the running mean, problems we encounter is that the running mean is very sensitive to outliers. One pole can fundamentally change the structure of the apparent polar wander path. It's very sensitive to the choice of the moving window, the moving average window. So this kind of serves as an hyperparameter that the user needs to fit, needs to select in one way or the other. And in general, running means are not very, very smooth paths. The splines regression is also very sensitive to outliers, unless some very strong notion of smoothness is imposed, which at the same time we introduce very strong biases in the path. Algorithmic implementation, there are not that many available codes to implement or to use this spline regression technique on the sphere. And something that it's important here is that this splines regression introduced a very specific notion of smoothness that may or may not have a geophysical foundation for it. So these are what I think a few points that are worth noticing about these methods. And in both cases, the underlying rotation, which is what we need to estimate in order to reconstruct the path motion of the plate, needs to be obtained a posteriori. This is what I mean when I say like these methods fit the trajectory rather than the underlying rotation of the plate generating this apparent polar wander path. Another approach is paleomagnetic Euler-Pole analysis, or just PEP. In this case, we assume that the rotation of a plate and then the form of the apparent polar wander path is being generated by rotations that are stable for significant large periods of time. And this gives rise to these particular paths that look like piecewise rotations on the sphere. So for many cases, this is very well funded based on empirical evidence. And I would say this is a method that includes like very strong geophysical assumptions of how the apparent polar wander path looks like. So this is another approach also to paleomagnetic Euler-Pole analysis. Now, motivations for new techniques. I would say for me, as a sort of a statistician, I always am surprised how difficult it is to obtain data, how difficult is for scientists to estimate paleopoles. So since data is scarce and paleopoles are difficult to obtain, I think it's worth rethinking about the mathematical tools that then we use to draw conclusions out of that data. So I think it's interesting, this question about how to estimate apparent polar wander path and address the difficulties that I mentioned before with the existing methodology. How to introduce multiple different physical constraints in the apparent polar wander path, like if you have some idea or some prior about how the plate has been moving over the years. Is there any way to include this information in the reconstruction of the APWPs? How to model the combination of multiple sources of rotation. So we know, like in principle, the movement of a plate can also be driven by, for example, true polar wander. So how can we model true polar wander in the apparent polar wander path directly? How to naturally account for temporal and directional noise, and how to automatically and statistically assess each possible model and its parameters. So this is for me the motivation for thinking about new methodologies for fitting apparent polar wander path. The proposal that we have is to introduce a tool to estimate apparent polar wander path that do not introduce numerical artifacts, that allows for multiple scientific hypotheses, just like the ones using in PEP analysis or in any other setting, allows automatic calibration of the model parameters, for example, the level of smoothness, and allows to include both uncertainties in time and space. So our suggestion is this package that we call SphereUDE, and I'm going to explain what UDE stands for in a few slides. Which is a Julia library that can also be executed from Python that relies on this technique called universal differential equations. So the next on the talk, I'm going to be introducing what this tool is and how do we estimate apparent polar wander paths using this tool. Good. So this is a cartoon example of the workflow of SphereUDE.jl. So we're going to start from spherical data, points in the sphere, paleopoles in the sphere. And what we're going to do is introduce a differential equation to model the path going through those poles, such that in the next stage we have this kind of smoothing path going through the poles. This path is going to be calibrated but by the use of inverse modeling techniques when we automatically recover the rotation that generated this path. And the last stage for this is regularization, which is when in statistics when we refer to regularization, it's just any kind of methodology that allows to constrain the possible space of solutions, for example, to include scientific assumptions. So let's go for the first stage, differential equation modeling. We're going to be thinking on poles that are going to be described by a certain age that can have uncertainty, and a certain direction, which is described by a unit vector in the sphere, in the three-dimensional sphere. And we are going to assume that each one of these paleopoles is distributed following a Fisher distribution, which is not a very constraining hypothesis. Other distributions can be considered in our workflow. We just pick the Fisher distribution for simplicity. And in this Fisher distribution, the concentration parameter kappa can be given by observations, or in principle can be also be calibrated. But in most of the cases, we're going to be thinking that we do have an idea of what kappa is for each one of the paleopoles. So using differential equations as universal approximators, what this means is that every possible path that you can map in the sphere, every possible apparent polar wonder path can be described by a simple, very simple ordinary differential equation that implies that changes in the apparent polar wonder path. So if x of t represents the position of the apparent polar wonder path over the sphere, the changes in that position are just given by the cross product between some vector L and X. So this is a linear system of ordinary differential equations in 3 dimensions. It's super simple. The good thing about this is that for every possible apparent polar wonder path, there's going to be an L of t that reconstructs that apparent polar wonder path. An L of t can be interpreted as a vector, which direction is exactly the Euler pole, and its magnitude is exactly the angular velocity produced by the rotation around that Euler pole. So this has like direct physical interpretation. And if you know L of t for a given apparent polar wonder path, you already have the rotation. Now, this just gives us like a way of constructing apparent polar wonder path. The question is, how do you find the one that fits your observations the best? So the inverse modeling part is what we use universal differential equations for. Here the UDE inside SphereUDE. So universal differential equations is a particular type of physics-informed machine learning techniques that is based on data-driven methods that allows to include physical knowledge, in this case, directly through the use of a differential equation, in this case, the one that I just showed you before. The philosophy behind universal differential equations is to embed a neural network inside a differential equation. So differential equations, it's the language in a sense of the physical sciences. They allow us to describe the evolution of physical system over time and space. The idea is to embed a neural network inside a differential equation such that the parts inside the differential equation that we don't know, we can learn them based on observations. So UDEs is kind of this intersection between physical modeling, numerical methods that we need in order to solve these differential equations and optimize all the variables, and data-driven models driven by machine learning. And the reason why we use neural networks is just because neural networks are known to be universal approximators. So in principle, every single Euler pole history can be obtained using a neural network. Something just technical, if someone is interested in a follow-up on this, is that these inversions are based on differential programming, which both differential to programming and physics for machine learning has been a hot topic in the scientific machine learning community, I would say, between the last 5 or 10 years. And there have been a lot of interest in developing differential programming models for the physical sciences in many, many different applications. So now the workflow looks like this. So we have the crosses in the sphere, which are observations. We have a smooth path described here, but the black line, which is nothing else than the solution of a given differential equation, where that differential equation is just changes in the path are just given by the cross product between L and U. And L is the Euler pole. So what we're going to do is to learn the Euler pole as the output of a neural network that takes as an input time. So this is just another way of learning a time-dependent function in a very generic setting where, in principle, we may or may not know anything about the form of the Euler pole, but since neural networks are universal approximators, every possible L of t can be recovered using a neural network. Maybe something worth mentioning is that the reason we use this differential equation is because this differential equation conserves the norm of the vector. So that means if you start from a vector located, in this case, in the south pole that has unit norm, so it's just a direction, for every single time after that, that vector will still be on the sphere. It will still have norm equals to 1. So it's the differential equation that preserves the norm of the vector, which is what allows us to do statistical spherical statistics, meaning observations always supported in the sphere. So the constraint about being in the sphere is introduced by this differential equation. The last step is regularization. That is, how do we impose different physical assumptions on top of this model? So in SphereUDE, we allow for different forms of regularization. In this case, we can impose a general form of regularization given by this equation, which is a combination of an integral of derivatives of the Euler pole plus some norm. So I'm not going to go much into the details of this, but just to say that this regularization allows you to regularize for small angular velocities. For example, if you have a constraint about what's the maximal angular velocity of a plate, allows you to fit smooth trajectories in a very similar way that what the smoothing splines do. And also it allows you to do piecewise rotation by introducing some form of lasso penalty, which is equivalent to doing PEP analysis. So in a way, what we like about this workflow is that all the different strengths of the different methods that I mentioned before can be combined together by just changing the type of regularization, and can be also be combined together. So the complete pipeline looks like this. We start with some ordinary differential equation to constrain data on the sphere. Then we use a neural network for universality. That means just to approximate every possible Euler pole as a function of time. We add regularizations to include physical constraints and physical assumptions. And finally, we just optimize all these pipeline, that is the parameters of the neural network, based on maximal likelihood estimation. So that, in other words, that's just a way of introducing the model and the observation noise into the model. So we can model the noise on the paleopoles and just try to find the Euler pole that best describe those observations between their respective uncertainties. So let's see some examples. So these first two examples are going to be synthetic. In this case, we have this curl curve, which looks like an upper and polar wander path that looks like this little curl that goes over itself, described at a non-stable Euler pole. So the Euler pole is changing time to time. And we have no regularization. So the way our results or our pipeline works is we optimize this. So we use a combination of different optimizers that are very, this is pretty much standard in the machine learning literature, applying like a very simple optimization first, and then apply something more complex for the second stage, so the loss really can go down. And at the end of the day, we allow we recover perfectly this upper and polar wander path. So in these two top two panels, the points are the observations, and you can see like the little line going through them is the result of the inversion. And you can also see how well you do in recovering the underlying rotation and the underlying Euler pole. This is a noiseless case, so synthetic example number one. Synthetic example number two is a example of how PEP analysis looks like. So in this case, we consider paleopoles sample from a true apparent polar wander path, like looks like the combination of two piecewise rotations plus noise. So from left to right, having more uncertainty in the location of the poles. And in all these cases, of course, when the noise is very low, the apparent polar wander path fits the observations very well. As the noise increases, it's more difficult to fit exactly the apparent polar wander path, but still the reconstruction is quite fair. There are a couple of artifacts in the inversion, so you can see these spikes here. This is produced by the neural network. It's something to fix, probably that I will probably fix at some point. For practical purposes, it's perfectly fine. Like you can just smooth out that signal, and the apparent polar wander path still will look like pretty much the same. And the last example that I want to show, and probably I will spend some more time discussing, is fitting the apparent polar wander path of Gondwana. So we grab the paleopole dataset also from Thorsby et al. 2012 for the supercontinent Gondwana. So that consists of around 194 poles for the last 550 million years. There's a little typo here. This dataset also reports the directional uncertainties. So we use the directional uncertainties. And this is a particularly very interesting problem, not just because there is real data for this one, but also because there are different reconstructions in the literature. So it's interesting to see how our methodology compares. So first, some results. So the two plots here are the same plots that I showed a couple of slides before when we have the reconstruction of Gondwana. And this is the reconstruction that we get using SphereUDE. So you can see that it's much more smoother. Here also in a different axis, you can see the latitude and the longitude of the apparent polar wander path and the poles. First, I comment on this thing going on here near the South Pole. Our path is far more smooth in this reconstruction, but probably more interesting is the lack in SphereUDE of recovering this little back and forth in the apparent polar wander path produced by this individual pole in the Ordovician-Silurian boundary. Our path is much smoother, and it has argued in the literature that a reason for this change in the apparent polar wander path could be because of true polar wander happening around that time, which is a perfectly possible explanation. In our case, we just find something a bit smoother, so definitely something to keep looking at and keep exploring. Something interesting here is like how to pick the right level of smoothness. This is something that you have to do with any kind of this methodology, how to pick the hyperparameters. So in our case, we just plot an L curve, which is just a way of plotting like the regularization cost as a function of the empirical loss. And usually, if everything works well, which is not always the case, of course, this plot should look like an L, and the knot and the edge of the L is usually the best choice of the hyperparameter. So for this case, for the reconstruction of Gondwana, this kind of is the case when you can see like the knot in the L corresponds to the reconstruction that I showed before. And as you go top and right, the reconstruction starts like either overfitting or underfitting the observation. So this also gives you an automatic way to pick in the right level of smoothness. To start finishing this presentation, I always like to mention that scientific software is always important. Spending time, spending a lot of time of the research writing code that can be reproducible and hopefully used by other scientists, and spending time testing and packaging these tools. And also building on top of existing tools. So in this case, SphereUDE is heavily based on a lot of tools in the Julia ecosystem. and also in tools in the Python ecosystem, such as PyMacPy. I do believe we make progress faster and better when working interdisciplinary, collaboratively, and community-driven. So always happy to connect with more people and work collaboratively. And as I said before, SphereUDE is a Julia library, but can be used from Python. So if you want to give it a try, or if you want to use it for your own research, you can do it from Julia, you can do it from Python, and you can do it from other programming packages too. Today, there is like ways to executing one programming language to the other. So that's a pretty cool feature that came up in the last couple of years. So the main takeaways, fixed for machine learning, it's a way of constraining data-driven models with physics. And it's this is what I do in my research. I like to develop physics for machine learning for different geoscientific applications. We introduced SphereUDE for apparent polar wonder path estimation, which also can be used for any other regression problem on directional data. People use this for bird migration, for cardiovascular data. So as long as data lies in the sphere, this tool is useful. And SphereUDE allows to model different apparent polar wonder paths depending on different hypotheses. So I find this very appealing because you can have all these different geophysical hypotheses working together in the same tool. And of course, it's an open source library that everyone can use and contribute to. Next steps, I'm interested in exploring, in particular, this nature of the different regularization terms that can be used in geophysical models. In particular, I'm interested in finding ways of reconstructing apparent polar wonder path that allow for both the estimation of potential true polar wonder happening for all the plates, for all the continents. At the same time, you can fit the apparent polar wonder path of each individual plate. So I think there is an interesting opportunity there of research. Introduction of non-paleomagnetic constraints to rotation. That's also that you can also think about. For example, constraints from seafloor spreading rotations. As long as you have the data, you can include these in this fitting procedure just to make your fitting procedure more accurate. Incorporation of time uncertainties and time registration in the model. Some time registration is this problem with you don't know exactly the age of something, but you can have like a vague constraint, which is philosophically different than reporting an age and giving a time uncertainty around that. So that can also be addressed with SphereUDE, hopefully with that much work. And something that is also interesting is quantifying the uncertainty on the whole path, on the whole apparent polar wonder path, and having an ensemble of paths to quantify how certain are about these reconstructions. So that's it. If people are interested, feel free to reach out. And I'll leave here the QR for the preprint and also the QR for the Julia library if people are interested. Thank you.
Reacting with applause for that. Yeah, thanks for the great talk. If anyone has any questions, either raise a hand in the Zoom call, or you can type your question in chat, and then, yeah, we can ask that. Okay, maybe I'll break the ice with a question. So at what level of the data hierarchy are you doing this fitting to? So are you doing this to sort of, you're just doing this to the pole level, or are you looking at like the individual data and then fitting to those? Because I know there's been some techniques recently that kind of have looked at using different levels of the data hierarchy to do the fitting. So what's your take on that?
For the examples I show here, we're doing everything on the paleopole level. That's something also we include in the preprint. You can do this at any level. You can do this at the BGP level, for example, because the problem we're trying to tackle here is like any technique that where you will, for example, will apply the running mean. No matter if you're applying that at BGP level or a paleopole level, you can in principle use this. You can use this directly at BGP level. So if you're just running a running mean for the BGPs, you can apply SphereUDE for the BGPs. What I think it's even more interesting is to change the likelihood model, like the probabilistic model behind, to account for the hierarchical sampling of the paleopoles and the BGPs and how the observations are collected. So that shouldn't be that hard. And then feed a SphereUDE on top of that, because if you just feed the running mean at the BGP level, or you feed SphereUDE at the BGP level right now, it's like, you can still feed the BGPs, but it's like you're still thinking that every sample is kind of independent noise sample at certain age, etc., etc. But you can even impose the constraint that actually the sampling is kind of hierarchical by just customizing the probabilistic model behind this. So that's also something I like about this. Is very natural, where every source of model uncertainty and observational assumptions came into the model, such that if you change that, you can just go and change the likelihood, change the regularization, change the hypothesis over the neural network feeding the Euler pole, etc., etc.
Okay. Any more questions? Any in the chat? There's one from Ethan Lopez. It says, what challenges do you anticipate when incorporating true polar wander into your models? I expect that you would introduce a lot more non-unique solutions that could be complicated.
The question answers the question answer itself. That's exactly right. The challenge you will have there is you're going to have a lot of equifinality between possible solutions, and that's what I think is going to be very interesting about thinking about the regularizations. So, for example, something that I think will be super interesting is like the regularization that you will apply to the true polar wander rotation versus the individual plate movement rotation are going to be very different. So, for example, if you expect true polar wander to be like an sporadic event, that's going to be a rotation that maybe gets activated during certain time window when then it's kind of off. So, for example, that's something you can include, and it's fundamentally different than the signal that you observe from individual plate movement. The other thing that it's the hope is that you can also feed like the different apparent polar wander path for the different plates kind of separately. True polar wander can be this underlying rotation that goes over a lot of them, while the other component is kind of independent of that. So that could be also like a way of disentangling these two contributions. But underlying, there is always going to be, yes, this problem that you may have a lot of equifinality between solutions. Reason that I believe it's very important to be able to report the uncertainties on these estimates. So, maybe some reconstructions will have true polar wander, some reconstruction may not have true polar wander. So at least you can assess, what's the probability that in this signal there is or not true polar wander, for example. But that's a very, pretty critical and interesting question to keep doing research on, I think.
Okay. I don't see any more raised hands. Oh, there's another one in the chat. Could you comment on the conundrum between assuming paleomagnetic data being constrained in time and space and separating it from the plate movement, when the paleomagnetic data location is actually inferred from plate movement models integrated back in time? And that's from Felix Garrick.
Oh, I think I got a little bit lost in the question. I will like to read it again.
It's in the chat. Shall I read it again?
No, let me. It's just that now I cannot find my chat window. Yes, can you read it one more time, please?
Thank you. Could you comment on the conundrum between assuming paleomagnetic data are being constrained in time and space and separating it from plate movements? And then it says, when the paleomagnetic data location is actually inferred from plate movement models integrated back in time. So I think this is an idea of like a VGP being inferred from, sorry, not clear. In the end, you're concerned that the paleomagnetic plate data is not independent of the plate movement. So it's the independence of the two. Yeah.
So, but what would be independent of what? The age and the direction, for example, or? Yeah, I'm not sure. Sorry. If I'm happy to follow up on that question, but I don't know exactly what it's referring to.
So there's a hand up from Christian Onoza.
Oh, hello. Oh, no, that's
No.
not working. Can you hear me?
We can.
Yes.
Cool. Yeah, sorry, my video doesn't seem to want to work today. Thank you for the talk. It's really good. I'm a total newbie at machine learning, and I'm trying to figure out how I can make use of it for time series data, so environmental magnetic records. And I've been using the Weka tool set from Waikato University, or that platform. But while you were talking, I was wondering how much of did you use some data for learning, for teaching the model? Did you have to do that in this case? And how much of it? So this is the thing I'm struggling with.
Yeah. So the data we use for training is the paleopolls we have. So for example, in the case of here, in the case of the Gondwana reconstruction, we're using the 194 from these 550 million years time window in the reconstruction. So the training is happening with what in machine learning is considered like low data regime. And that's perfectly fine, because one of the strengths of physics-informed machine learning versus machine learning approaches is that since we're introducing a lot of physical assumptions about in this case, a form of the apparent polar wonder path, in principle, you may need less data to train this model that if you're just using like a general machine learning technique. So for example, just feeding a neural network on top of that. So the training is happening directly on the paleopolls, just as the running mean. If you think the running mean is also like a learning algorithm, that will be happening also at the paleopoll level. So the data to train is always the paleopoll. You can imagine cases where even you go one step further and you separate that data into training, tests, etc., etc. So the same pipeline can apply here. But in principle, we always going to be in these physics-informed machine learning settings, and particularly in paleomagnetism, in cases where we don't have like thousands and thousands of observations, probably we have less observations, but the physics kind of allow us to constrain a bit more the model.
Yeah,
Does that
that's
answer the
really
question?
Yeah, that answers the question almost perfectly, because I mean it shouldn't be a linear system. It's a chaotic system, really, the paleo wonder path, aren't they? So we're trying to learn more about that. Yeah. No, it's very interesting. Thank you.
Of course.
I think if we've got no further questions, then I will finish up the meeting. So I've just got a couple of things to say for housekeeping, and hopefully my Zoom doesn't crash when I do this. But there we go. Okay. So our next talk will be on the 29th of October, so in 4 weeks' time, by Christian, who just asked a question. And it's going to be on pushing environmental magnetic records to the limit, Younger Dryas drought and IPO climate modulation during the Antarctic cold reversal in New Zealand. So catch that. And if you can't make that, or if there are any other of these seminars that you haven't managed to catch up on, we have a YouTube. It's just called MagNetZ on YouTube, and we've got over 135 presentations to view. So if there's anything that you've missed, feel free to have a look at it there. And with that, I think we can stop the recording, and if people want to stick around, we can move on to a sort of informal chat session. All right.